There's been a breakthrough that's completely changing the game for AI. It's moving us away from these mysterious black boxes and towards something we can actually understand. This is a really fundamental shift in how we build and, more importantly, how we trust these systems.
The big dream has always been an AI that can not only give an answer, but also show you exactly how it got there. For the longest time, this has been a massive challenge. You see, most of today's AI models are what we call black boxes. They produce incredible results, for sure, but the why behind their decisions has been totally hidden from us. And this right here, this is the perfect way to picture the difference. A normal AI network is this ridiculously tangled web of billions, sometimes trillions of connections. Trying to trace a single line of reasoning through that, it's basically impossible. But a sparse network, well, that's like a perfectly organized filing cabinet. Everything has its place, with clear, specific pathways for information. It's a system designed from the ground up for clarity.
All right, so here's what we're going to cover. We'll start with that black box problem, then get into the really elegant solution called Circuit Sparsity. We'll see it in action, talk about the trade-offs involved, and then finally explore why all this transparency is so incredibly important for the future of AI.
Okay, so that brings us to the core idea here, circuit sparsity, and how it's the key to untangling that incredibly complex web.
The key technique is something called forced sparsity, and it's a really clever idea. Instead of letting every single neuron connect to thousands of others, you intentionally set most of those connections to zero while the model is training. What this does is it forces information to flow through a much smaller and more deliberate set of pathways.
And the scale of this change is it's huge. We're not talking about a small adjustment. In a standard model, one neuron might be connected to thousands of others. In one of these sparse models, it only connects to a few dozen. This isn't some minor tweak. It's a complete re-architecting of the network, and it radically simplifies how everything works inside. And what you get from all this simplification are these little traceable routes we call circuits. Each one becomes highly specialized and responsible for a single, distinct task. That makes its job really clear, and, for us, totally understandable.
Okay, let's move away from the abstract for a second and look at a real-world example to see how one of these circuits actually gets the job done.
This is a really cool one. Researchers trained a sparse model on Python code, and out of that training, a specific circuit emerged that was dedicated just to matching quotes. And its logic is perfectly clear. Step 1, it detects if a string starts with a single or double quote. Step 2, it holds on to that information. It remembers the quote type. And finally, step 3, it predicts the correct closing quote. A simple, clean, 3-step process.
And get this is the incredible part. That whole job is handled by just 2 neurons. 2! It just goes to show you how incredibly efficient and, more importantly, how traceable these specialized circuits really are.
Trying to get this kind of transparency in a typical dense network, pinpointing the exact 2 neurons responsible for one specific behavior, it's just not possible. You'd be totally lost in that tangled mess of connections.
But, there's no free lunch. This whole approach comes with a trade-off, and it's important to understand the balance between this amazing new clarity and the model's overall capability.
So this chart lays it out pretty clearly. As you crank up the sparsity, meaning you set more and more of those connections to 0, the model becomes way easier to interpret. That's the huge win. But you can see there's a slight dip in its overall performance. So the goal isn't just to max out sparsity, it's about finding that sweet spot that gives us the most transparency for a level of performance that's still really good.
All right, let's zoom out, because this isn't just a neat technical trick, it has huge implications for the bigger picture of AI.
The upsides to having transparent AI are just massive. We're talking about building real trust in these systems, especially in high-stakes areas like medicine or finance. We absolutely need to be able to trace their decisions, understand why they make mistakes, and fix them. That's how we ensure they're safe and reliable. And ultimately, this kind of understanding is what will let us confidently build and manage the even more powerful AI systems that are coming down the line.
And really, this quote just nails it. So much of the fear around AI comes from its black box nature. But if we can actually see and understand what's happening under the hood, we can make sure these systems are aligned with what we want them to do.
So here's the bottom line. The future of AI, the next great leap, isn't just about building bigger and more powerful models. It's about building clearer ones. The future of AI isn't just about raw power. It's about creating systems that are both incredibly powerful and profoundly understandable.